I'm just going to give you guys a couple more minutes to get logged in and get everybody on board. I appreciate everybody coming today and taking time out of your day to view this webinar, and I hope it's a success and you guys really like it. I got sort of introduced to Rich back probably about 2 months ago at this point, and he and I kind of had a phone conversation and hit it off, and we ended up staying on the phone for like an hour and a half just talking about pharmacy stuff and clean rooms and all sorts of things. And sort of out of that conversation came this idea of doing this webinar and talking about environmental monitoring and mitigation strategies specifically. And we got to brainstorming and talking through this whole thing. And I said, I think there's a lot of people that could benefit from just a down in the weeds version of how to actually go about doing and setting up a risk-based environmental monitoring program. And with that, we can sort of introduce something that you also bring to the table, which we'll get to later on in the presentation. When Rich comes on, he's going to be talking about a particular device that I think is really innovative and extremely helpful for those that are looking to mitigate issues that they may be having temporarily in their clean room, or even as a strategy to utilize for when you're doing construction in a clean room. Or there's many different scenarios and use cases for what Rich is going to talk about, but I'll leave that to him. So let's see, we're about 5 after now at this point. I think I'm going to go ahead and get started. There's looks like 63, 64 people are still logging in, but let's just go through our first couple slides. First couple of slides are pretty introductory anyway, and there's some polling questions that I'm going to put out to you guys. So let's go ahead and get started. My name is Seti Pasquale. I am a pharmacist and board certified sterile compounding pharmacist. And I do a whole bunch of things. Right now, I just started working as a consultant for Visant, which is a consulting firm that helps out hospitals and health systems and 503As, 503Bs, you name it, they do it. I'm also co-owner of a company called Lyceum LLC, a company that specializes in the creation of ACPE accredited video-based content for sterile and non-sterile compounding training. Other than that, I have nothing else to disclose. And neither is Rich. Rich is a mechanical engineer by training, and I can let him introduce himself when he comes on later in the presentation. But yeah, so let's go ahead and get started with some of our polling questions. So hopefully I put this together right, and these actually work out. So I'm going to launch the poll. None of these questions are very difficult to answer. They're really just for my own edification, and just kind of want to engage who the audience is. So the first one is, what area of the industry do you work in? 503A, 503B, hospital, pharma, other. Next question is, what is your job role? Operations, production, management, quality, other. And have you ever been involved in responding to an FDA 483? So I'll give you guys another few seconds to answer there, and we'll get the results. Okay, got a pretty good portion of you guys voted. So I'm going to go ahead and end the poll, close that out, and hopefully this is sharing the results. So it looks like there's quite a few people from hospital actually, which is great. I'm very glad that there's a whole bunch of hospital health system people on here today. Some from 503A, very few from 503B. What is your job role? Mainly management is on board here, so that's good. I think a lot of this stuff has to kind of come, especially when we're talking about this, has to come from top down. And this is, while this is going to give you a high level overview, this is also a pretty detailed presentation on exactly how to go about implementing a risk-based environmental monitoring program. And then the final one, have you ever been involved in responding to an FDA 483? So 16% said yes, 84% said no. So I'm not going to get too much involved in how to answer an FDA 483. I have done that several times as a consultant working with 503As and Bs. I will say there's definitely a certain format. So if you ever do come in contact with the FDA and have to respond to a 483, let me know and I'm sure I can help you. So but I'm gonna go ahead and close out, stop sharing that poll, and let's get moving. So here are the learning objectives for today. By the end of this, you'll be able to explain what a risk-based environmental monitoring program is and what considerations are used to implement. You'll be able to discuss how to determine where, when, what, and how often to sample based on risk. Also discuss the 3 different types of sampling and the importance of each. You'll also be able to discuss the different types of growth media and devices used to sample and the use for each of the 3 types of growth media typically utilized. And lastly, you'll be able to explain how to investigate a contamination using 3 tools and to discuss the 8 phases of CAPA, Corrective Action, Preventative Action. I got a question, will the slides be shared after the presentation? No, the slides will actually not be shared after the presentation, I'm sorry. But I will be, this is all being recorded, and I will have a way for people to look at the presentation again if they wanted to. But the slides themselves are mine, and I don't really give those away. Sorry about that. So here's a general overview of the presentation. We're going to go over the top FDA 483 observations, and you guys are going to see a little bit of a trend there. From 2016 to 2020, you're going to see a lot of common things, common themes throughout. Then we're going to talk about a risk-based environmental monitoring program and contamination control. We're going to go through an excursion, how exactly to remediate that. We're going to go through the process of a CAPA, and then we'll kind of have some final thoughts on the whole presentation, and we can take questions from there. So let's go ahead and get started. So here's the top 10 list of 2020. This includes all observations from 503As and 503Bs. You can see that the top one, and this is year after year, the top one is always procedures not in writing fully followed, which means either you have a procedure, you're not following it, or you're doing something and you don't have a procedure for it. So one of those two situations usually. And then the second one, which is what we're going to be talking about, is investigations of discrepancies or failures. And this presentation was actually morphed from another presentation I had, which I had a bunch of different 483 examples of different locations, facilities failing to look at and fully investigate issues specifically with their environmental monitoring program. But you'll see here in 2016, 2017, 2018, 2019, 2020, it's either the number 2 or number 3. So, it seems like we're not getting necessarily any better at it as an industry. And again, I just want to point out that those FDA 43 numbers are not a collection of just compounding pharmacies. That's 503As, 503Bs, big pharma. That's the whole picture. So it seems that across the board, we as a pharmaceutical industry have an issue with investigation specifically. So here again, just to reiterate the top 5 for 2020, investigations of discrepancies or failures is number 3. So here's how this is going to go. We're going to go through our environmental monitoring program overview. We're going to talk about a risk-based approach, the types of sampling, air, surface, and personnel. We're going to talk about the different types of media, investigating excursions, and then remediation and mitigation by way of CAPA, corrective action, preventative action. And if many of you are not familiar with CAPA, you hopefully will be very well versed in it by the end of this. So risk, when I talk about a risk-based environmental monitoring program, this is what I'm talking about. Risk is a combination of the probability of an effect to occur and the severity of the effect to occur, or that's occurring. So the probability, how likely is it that X is going to happen? And when X does happen, how bad does that impact? In this case, we're typically talking about making sterile products or some kind of pharmaceutical product. How is that going to affect our patients? So with that in mind, where, what, and how often should we sample? And that kind of depends. It depends on a few different factors. Depends on your product, your preparation, whether you're starting with non-sterile ingredients or if you're starting with sterile. Depends on the complexity of your process, how many operators are involved. And of course, to some degree, depends on standards and guidance. There's 797 and FDA guidance out there that talks about the different types of sampling, and how often, how frequently, and what should be sampled and where. Of course, the way I'm going to be talking about it, if you're using a risk-based approach, in many cases, you're going to be going above and beyond what any of the standards say. And just as a forewarning, if you see a cat tail go across the screen, it's just my cat that's sitting on my lap. So sorry about that. Just apologies ahead of time. So here are the different types of sampling. We got air, and we can break that down into 2 different types: viable and total particle counts. Which total particle counts are typically called non-viable, but I don't really like that term. It's not as good a descriptor as it should be. Non-viable infers that it's basically just counting particles that are not alive, which is actually not true. A particle counter is counting all particles of a particular size, whether they're alive or have no microorganisms attached to them or not. So just a little bit of a name change there. Surface samples, we're going to talk about contact or touch plates, and then personnel. Typically within the 503A hospital health arenas, we have glove fingertip testing. People are fairly familiar with that. In 503B and in CGMP, they also do post compounding or post manufacturing chest, forehead, and sleeve sampling as well. So it's a little bit more intense to ensure that operators are following good aseptic technique and good behavior throughout the entire process. Here's a look at some of the sampling devices. On here, most of these things are actually viable samplers. The only one that is a particle counter is the one in the bottom left-hand side of the screen. The other ones you might be familiar with, you might have seen like in the top right-hand side of the screen is a SAS sampler. That's used a lot of times with companies that are coming in to certify your room. They're not too pricey. I want to say they're in the range of like $3,000 to $5,000. They're simple to use, simple to set up. And that really applies to all of these pieces of equipment. If there's one thing I want to get the point across is that if you go ahead and buy any of these pieces of equipment, they're all fairly easy to use and could be there. Don't get me wrong. There's definitely things that you do and don't want to do with these, like touching the sampling head. The sampling head of the viable air sampler is where the air is coming through. So you don't want to put your hand over that while it's testing, especially, nor touch it directly with your gloves or anything to potentially contaminate your sample. So, and then the particle counter on the bottom left-hand screen, part of the screen is also really relatively pretty easy to use. You essentially turn it on, you have it in a particular location, and it counts particles. That's about it. But there's a whole lot more to it in terms of the information that you can gain from all these different devices. So when we're talking about particle count specifically, 797 says that we need to do particle counts at least every 6 months under dynamic conditions. And dynamic conditions, so let's define that. Dynamic conditions is typically you doing a simulated compounding scenario. Typically, you'd want to do like your worst case scenario. You're taking some syringes, taking whatever your worst case scenario is. The same number of operators that would normally be in there, move around the clean room while this is going on. And you should really honestly be involved in and be a part of the certification process. Not only will it give you some hands-on experience, but you can ask the certifier questions. You can see how their equipment is working. You can ask them specifically about the report that they're generating, what all these numbers mean. So I highly recommend people getting more involved in their certification process. But really how this is all calculated, the number of samples depends on the size of the room. And down there you see a table which comes from ISO 14644. And essentially it has the square meters of a room on one side and the number of samples that you're going to test on the other. So typically we're dealing with a room that's a square, and we just essentially divide that up into a grid. And if it's an odd number of samples, and we'll have to get an odd number of samples. So be it. Typically, like that'll be like a five side of a die. You'll get one in the middle and four in the corners. But that's it. It's that simple. They're basically just looking at the size of your room and generating a number of air samples, particle counts, based on this standard ISO 14644. So here are your limits for the different ISO classes. And ISO 14644 recommends that you do in one location. So remember, I just said in a room, you're going to have several locations that you're going to test. ISO 14644 alludes to having several samples done in one location and then taking the average of that sample. And then for the entire room, once you get done collecting samples for the entire room, you're going to average that. So it really should be how it should be done is that you would do 2 to 3 samples in each location, and then you would take an average of all those samples. So it'd be an average of all the averages. And this is strictly quantitative. You're just counting particles. It's a general test. And where can this actually come in handy? Well, where it comes in handy is that you'll know that if there's a large number of particles in your room, you can bet that there's probably a portion of those are going to be are going to have microorganisms attached to them. So that begs the question: where would you put a particle counter if you had one? Would you only use it while you're compounding? Would you put it in your PEC? Would you put it near your PEC? Would you put it in frequently visited areas inside the clean room? And that depends. It depends again on. We're always going to come back to risk here. It depends on the risk of the compounding procedure. Typically in GMP environments, they will have these just running all the time. And a good portion of the time, when of course they're not in operation, they are just counting 0 particles over and over again. But it could be used as a good metric for potentially telling us when to do viable samples. So I kind of already alluded to this in a previous slide. Particle counts tell us you have to first remember that microorganisms are attached to particles. They're attached to a certain size particles. Most frequently, we're looking at 0.5 micron, which is the typical size particle that you'll find a lot of microorganisms attached to, or larger. And this can tell you one of several things. Are we wearing the appropriate garb? Are we wearing garb appropriately? Are we wearing the appropriate level of garb? Are we just using a non-sterile gown versus 100% covered up, no skin whatsoever exposed? And then it'll also kind of give you an idea of operator behavior and technique. If there's the more you're moving around in the environment, the faster you're moving around, the more particles you're shedding, and the more particles that are being brought up from the floor and just aerosolizing in the air, and it's gonna be picked up by that particle counter. So it's really just a general indicator of the area, of the state of that clean room. It does not tell you anything about microorganisms or anything like that. So a single particle count, and this is where I kind of disagree with 797 only wanting people to do particle counts every 6 months. A single particle count really doesn't tell you anything. It's a snapshot in time, and that's it. It just, for that brief moment that it's looking at your error. Great, you had this many particles in your room passes. Awesome. But what about during actual operating conditions? What does your air quality look like then? Well, if you have a particle counter set up in your clean room, like I said, there's a lot of different things that you can pick up on. One being the fact that, and by the way, this is an Excel spreadsheet that I made myself, and these are all just randomly generated numbers. But I will say that there is a trend here, is that the higher the particle counts are, you're going to start to see some colony forming units pop up if you're also doing viable sampling at the same time. So again, that sort of infers that there's definitely a relationship between the number of particles in the room and the number of viable organisms, microorganisms that are in the room as well. So there is real actual data that can come from this that can be very useful, especially when used in combination. So for viable air sampling, again, 797 says every 6 months. And unfortunately, there's no great guidance that says specifically how or when to do viable sampling aside from certifications. And one note here is that if you look at your certification report, I challenge everyone today, especially since we have a majority of people from hospital, pull out your report from whatever drawer it may be in, and take a look at it, look for the viable sampling, and ask yourself how many viable samples were taken. Now, remember, I said that there's a certain number of non-viable or total particle counts that need to be taken. However, there is not necessarily a set number of viable samples that need to be taken. So what happens, a lot of times when certifiers are doing certifications, they're basically duplicating, because they don't have any other direction to do anything otherwise. They're going to take the same number of viable samples that they took of total particle counts in the same grid and everything, and which equates to you or your hospital or your company paying more money for all that. Because if any of the viable samples come up with any growth, they usually have to send it off to a third-party lab, which costs them money, which in turn costs you money. And so yeah, check that out, and don't be afraid to say, hey, I don't think we need to do as many viable samples. Why don't we do viable samples in the room, like maybe in one place in the room that's utilized a lot, and then let's do one sample inside our hood and call it a day. So you do have the flexibility to say that to your certifier, and they will they'll do whatever you ask, basically. So not as much flexibility with the total particle counts, but with viable samples you do. So think about risk when it comes to viable sampling. And I already kind of just said this, areas that we are typically operating around, maybe we're going from one table and taking stuff off that table and then bringing it into the hood, of course, wiping off any materials before it goes into the hood, and sanitizing our gloves, of course, before we go back into the hood. So where and when would we sample? Well, again, this comes back to risk, the risk level of compounding. if you're the compounder that is doing something from starting with non-sterile ingredients and you're going through a filtration process, it might be a good idea to have a viable sampler in the hood potentially, hopefully not anywhere where you're disrupting airflow necessarily, but in the hood that would be able to tell you whether or not there's viable uh, any viables after the fact. And of course, the one drawback to viable air sampling is that it's retrospective. So you have to take the plate out, you have to put it in an incubator. You have to wait at least usually you can start to see some growth after 18 to 24 hours, depending on the organism. But you usually want to wait 48 to 72 hours. That's what 797 says. Um, and one other thing about viable sampling that's kind of nice is that it's qualitative and quantitative. So it's qualitative in the fact that you're able to take that sample out of the incubator. If there's colony forming units or CFUs on the sample, you can send that off. You can get those organisms identified, and that will give you a good idea of potentially what direction you should steer your investigation toward, where the source of that microorganism came from. And of course, it's quantitative because there's the number of CFUs could more or less tell you the how bad of a contamination you're having in an area. So here are the action levels. According to 797, here are the action limits for viable air samples. So if you have greater than 1 in your ISO 5, this is usually your PEC, your primary engineering control, you're going to want to investigate that. Greater than 10 in your ISO 7, which is typically your room, or in an ISO 8 area, which could be your ante room. If you have any greater than 100, you'll definitely want to investigate that. So yeah, those are the limits that we have to abide by according to 797. But I want to introduce another standard that is also a USP standard found in the USP Compounding Compendium that actually doesn't count the number of CFUs. Rather, it looks at what's called a contamination recovery rate. And a contamination recovery rate is simply, again, it's not looking at the specific number of CFUs, but just the fact whether there is growth of any kind whatsoever over a period of time. So, if you have 100 samples and one of those samples over a period of 100 days, one of those samples had 1 CFU or 5 CFU, doesn't really matter because, again, regardless of the number of CFU, then you have a 1% contamination recovery rate. And so 1116 also gives us suggested contamination recovery rates based on the type of sampling we're doing and the location we're sampling in. So of course, the lower the ISO class, the lower number of the ISO class, the higher the rating of the classification. You're going to want way less of a contamination recovery rate. In an isolator or a restricted area barrier access system, you're going to want less than 0.1% of the time. You're going to want to have any recovery of any growth whatsoever. ISO 5s less than 1%, ISO 6 less than 3, ISO 7 less than 5, and ISO 8 less than 10%. And it kind of goes across the board whether you're sampling, doing active air sampling, subtle plates, contact plates, or a glove or garment. The numbers basically stay the same within the ISO class. So, and there's, you know, I really like using Excel, a huge fan of it. This is another portion of the same spreadsheet that I showed you earlier. You basically, I made it so that I could have a drop down box and pick the ISO class and what type of sample. And then as I'm filling in the number of CFUs on a daily basis or whatever, um, there's another area of the spreadsheet that's calculating the contamination recovery rate. And what'll happen is when it exceeds the recovery rate for that particular sample type and ISO class, that box where the percentage is in actually turns red and says, you have exceeded the contamination recovery rate for this area. So, so yeah, there's a lot of neat things you can do with Excel. I'm going to show a couple other pieces of this Excel spreadsheet in just a second. Here it is. So this is basically the entire spreadsheet. You know, up top you have a graph of all particle counts and CFUs. The red, there's actually a red, yellow, gray, and green lines going across. And while we do have according to 797, we do have set action and alert limits. You can actually, there's sort of out there in literature, there's ways to calculate your action and alert limits based on the sampling that you're doing on a daily or weekly basis. So in this particular spreadsheet, it's actually counting in real time and calculating my action and alert limits for me as time goes on. And I have columns there for organisms, which are housed with I think 700 different organisms. And then based on the organism, it'll then populate a source. If you're keeping really good track of your particle counts, and say you have like a video inside your, or a camera inside your clean room, you can actually pinpoint, okay, well, we got a really high particle count at this point, at this exact time, what was going on there? And then, you know, I have a little drop-down box of different scenarios. Operator was moving too quickly, was shuffling their feet, open the door, close the door, yada, yada, yada. So this is a neat little spreadsheet, and took me a little bit of time to make all that, but it's a lot of fun. I love Excel. So again, USP chapter 1116 also gives us a frequency, a suggested frequency of sampling, which is going to be very different from what you're seeing in 797. So active air sampling in your clean room, in your RABs, restricted access barrier systems, you're gonna be doing it at least active air sampling at least every operational shift. Surface monitoring at the end of an operation. All sampling at the each operating shift, and in non-adjacent aseptic areas, just once per day. And then of course you can read the rest for isolators. You know, inside your isolator, you're going to do it once per day, surface monitoring at the end of your process or procedure, and then non-aseptic areas surrounding the isolator once per month. And there's the, I've already shown this, but there's the suggested initial contamination recovery rates. So again, sort of comparing, contrasting the two different standards. You're going to use action limits. And by the way, if you're just a 503, I don't mean to say just a 503A. If you're a 503A or a health system, you're basically have to follow what it says in 797. However, if you wanted to follow that which was just seen in 1116, you can certainly do so because the amount of sampling is much greater in 1116 than it is in 797. But if you exceed any of these action limits for these ISO classes, greater than 1 for 5, greater than 10 for 7, greater than 100 for 8, you are going to want to do an investigation. I see that I'm getting questions, and I will get to all your questions, by the way, but I'll get to them at the end. I promise I'll answer all the questions. So I am seeing all those questions, by the way. So this is just me showing off my my silly spreadsheet that took me hours to do. Again, I'm able to put in the 5 CFUs that were identified as Bacillus cereus. They're ubiquitous in nature. Dissemination of spores via aerosols and dust contributes to contamination of indoor environments. So when you're doing an investigation and Bacillus cereus comes up, which is a gram positive, you can get an idea or a sense of maybe where that's coming from. So it's ubiquitous in nature, meaning it's coming from outside. Is it coming from one of your operators? Maybe they haven't gowned or done hand sanitization properly. Perhaps they're not wiping off materials as best they could. It's sort of, again, I'm going to go a lot further in depth on this a little bit more in the presentation, but it definitely gives you an idea and starts you on the path to investigating the root cause. So contamination recovery rates versus action limits. Contamination recovery rates gives a better picture of the state of your clean room over time rather than looking at isolated incidents. So if you get, 5 CFU one day, and then, the rest of the time, so let's just say you're doing sampling on a daily basis, and on one particular day you got 5 CFU, that's not indicative of the overall state of your clean room. That's simply a snapshot in time for that particular time. And it's, if you were to get 5 CFU or 3, then 5, then 2, then 3, day after day, then that's maybe more of a little bit of an indicator. But you really can't get any real great information if you're doing any kind of viable sampling, be it surface or air, just doing it once a month or once a quarter or once every 6 months. It's almost, dare I say, useless information, and does not give you a very good picture over time of the state of your clean room. But if you use contamination recovery rates and action limits in combination, that can really help you identify trends and where a contamination came from. So let's move on to surface sampling. Surface sampling, according to 797, says surface sampling shall, which means must, be performed in all ISO classified areas on a periodic basis. Okay, so periodic basis. Let's see what else they have to say. Sampling can be accomplished using contact plates or swabs, and it must be done at the conclusion of compounding. So it says first on a periodic basis, but then goes on to say that it needs to be done at the conclusion of compounding. It doesn't necessarily say where it should be done, but I'll give you a little hint to that. It should probably be done in your ISO 5 hood or your primary engineering control. Maybe not just in one place, but a few places where the most critical spots were when you were compounding. that's where you'd want to sample. And of course, if you're touching, just I have to say this, if you're using contact media like this, you make sure and clean the surface after you sampled, because you don't want growth media just sitting on your most critical parts of your clean room. So, and this is not taken from the revision of 797 that's been sort of withdrawn. This is from the old 797 that is still currently active. So really, you should be doing surface sampling at the conclusion of compounding. Surface sampling technique, there's just a very few steps here. It's pretty easy. You have a contact plate. You're gonna take the cover off the contact plate. Using a rolling motion, you're gonna roll it onto the surface like that, and you're gonna replace the cover, making sure not to touch your gloves to any of the media. You don't want a false positive. You're trying to get a real good idea of whether there's growth on whatever your surface you're sampling, and you definitely don't want to touch your gloves to the growth media. So taking off that cover and putting the cover back on, you want to make sure and be very careful. After that, you're going to then invert the plate so that the media is on top, and so that when you put it into the incubator, typically when you incubate samples, you'll get some condensation. And if you have it so that the media is on the bottom, that condensation can drip onto the media, and that's just not a good scenario. So you always invert the samples when you put it into your incubator. And that's it. Like I said, this is pretty simple stuff. And again, I didn't know, I kind of forgot, I threw this in. Make sure and clean the surface afterwards. You don't want any residue from growth media on the surface. So what's the value of surface sampling? Well, let's think in terms of particle size. We talked about particle size when we were talking about the particle counters. They're counting typically 0.5 micron size particles and larger. These size particles are usually suspended in the air, and that's where you're going to pick up your viable sampling is going to pick up a lot of that, a lot of those size particles. The larger size particles, like 5 micron and larger, are typically like skin particles, dust particles. Those are going to settle on surfaces, and that's where surface sampling comes in really handy. So by doing both in combination, you're getting a really good picture of what's going on in the clean room. Again, if you're, depending on what your policies and procedures are, but you should be wiping off things before they come into the clean room. Of course, gowning and garbing is really important. Operator behavior and technique is really important. All of these things, if you're not doing these things on a routine basis, there's absolutely no way that you can have a good picture of the state of your clean room. And then on top of that, you're also not able to potentially improve your own processes and procedures. So really, I see environmental monitoring as a way to improve your overall processes and procedures of your operation. You may have one operator doing one thing and another operator doing something else. And again, without any data to go by, you don't really have any leg to stand on when and if the FDA was to come in and see what was going on. They're going to ask you for your environmental monitoring sampling. And if you don't have that, then that's when the scenario comes to play where they may ask, they can only ask you, but they may ask you to recall an entire year's worth of lots of product that or preparations that you made. So that's, yeah, not a good headline scenario you want for your pharmacy or hospital health system. So again, surface sampling, here are the action levels for surface sampling. Again, if we exceed action levels for ISO 5 greater than 3, ISO 7 greater than 5, ISO 8 greater than 50, we want to identify those to the genus level. And you have to, and it also goes on, I highlighted this entire portion of the paragraph because it goes on to say that some examples of corrective action include process or facility improvements, personnel training, cleaning and disinfecting, HEPA filter replacement and/or repair. So basically it's telling you that you have to investigate, find the root cause, and then address those issues. And it might not just be one root cause, it could be multiple. It could be a combination of cleaning and disinfecting. Maybe you're not cleaning as frequently as you could be cleaning. And again, you wouldn't be able to identify that with sampling every 6 months. Maybe on a weekly basis, if you're sampling just prior to your weekly clean or just prior to your monthly clean, and you're getting a whole bunch of, you're seeing a whole bunch of CFU pop up, then that may be indicative that you should be cleaning more frequently. Or it could be a personnel issue. The whole point here is that the more data that you can collect, the better you are to be able to investigate any issues that are going on with your clean room, and the better, more legs you have to stand on when and if any regulatory agency, State Board of Pharmacy, comes in and starts asking questions. So again, 1116 also addresses surface sampling, and I highlighted that there. I've shown this this chart now, I think at least 3 or 4 times, so you should be fairly familiar with it. So there you go. And again, it emphasizes how often you're seeing a contamination, not the number of CFU. So there's a difference there. 797, they're looking at the number of CFUs. 1116, they're looking at the number of times any kind of growth, regardless of the number of CFUs are present. So personnel sampling, you have glove fingertip thumb sampling according to 797. It says initially 3 times, needs to be performed 3 times prior to getting access to compounding, and you must have a 0 CFU result. And let's just address this real quick. That means garbing, the whole garbing, gowning process, hand sanitization or hand hygiene, and then putting on your gloves, that has to be done from start to beginning 3 times in succession with 0 CFUs present in order for an operator to gain access to the clean room. And then thereafter, if you're doing low and medium risk compounding, you only have to do glove, fingertip, and thumb sampling every year, every 12 months. If you're doing high risk using non-sterile ingredients, you're going to be doing that every 6 months at minimum. Now, you may, like, these are the minimum things that you have to do. If you're doing something very high risk, I wouldn't recommend doing glove fingertip sampling just every 6 months. This is more of a verification that your operators are able to properly gown, garb, and put on sterile gloves without contaminating them. But from the point of view of actually gaining information on whether or not each individual compound that you're putting out has a risk for contamination, that would really need to be done after each compounding procedure. So sort of like 797 indicated that you're supposed to be doing surface sampling at the end of each compounding procedure. I would say the same thing for glove, fingertip, and thumb sampling. While these are minimum rates for doing these, I would really suggest, depending on the risk level, that maybe you're doing these every day, every shift, once a week. It all depends on the risk level, and your own policies and procedures can really dictate that. For the every 6 month and annual ones, that for the operators that have already passed the initial, you're allowed to have a total of 3 CFU between both hands, and still pass. And just to remember that touch contamination is the highest risk for contamination of a compound, which is kind of why I just got on the soapbox about doing it maybe perhaps after every compounding procedure, depending on the risk level. Your operators should be sanitizing their hands very frequently, of course, every time they go back into the isolator or hood or whatever, into your ISO 5 primary engineering control. They should be sanitizing their gloves. Should be. Does that actually happen? Well, you don't really know unless you're sampling the gloves thereafter. So again, I'm just sort of reiterating my point that, I think it's always better to do a little bit more. And none of this stuff is so expensive that you're going to be breaking the bank. These plates are, they range $1 to a couple dollars a plate, depending on where you're getting them, from, who you're getting them from, and what brand you're getting. But getting more into like the GMP space, they do other sampling of their garb, forehead, sleeves, and chest. And what's the value in sampling garb? Well, you're able to assess the operator's behavior and technique. Are they taking their gloves and touching different parts of their body during the procedure? Your sleeves, your chest, and your forehead are all have that potential impact to be inside the hood just slightly at one point during a compounding procedure, which of course increases the risk for contamination, which is why they have you, in GMP world, they have you do forehead, sleeves, and chest. And 1116, again, here's that same chart, and there's the contamination recovery rates. And emphasizes how often you're seeing a contamination. So the different types of media. There's 2 different types of plates that you're going to see in surface sampling or in air sampling. The 65 millimeter are usually smaller, obviously, in size than 100 millimeter plates. These are the contact surface plates. They can also be used in some air samplers, so they're not just necessarily used for contact surface. They can also be used in active air samplers. The 90 to 100 millimeter plates are the ones that any of the air samplers that I've ever used fit the 100 millimeter plates. So you're going to use those plates for active air sampling. If you're going to do any kind of swab, you're going to swab an area and then apply the swab to the plate. And of course, glove, fingertip, thumb sampling is done with these larger plates. So yeah. The different types of growth media. So there's, if you read between the 797 2019 revision and the 797 current active form of 797, there's some differences, and I've kind of notated those differences here on the chart. But the most prolific or abundant media that you're going to see is tryptic soy agar. Tryptic soy agar is a general growth media that can be used actually for both bacteria and fungi. However, there's different lengths of time that you need to have for growing fungi. Fungi are typically slower growers, and they need to be incubated for a longer period of time, typically 5 to 7 days. For tryptic soy agar, if you're using them for both bacteria and fungi, what you'll want to do is put it in the incubator for between 30 and 35 degrees for 48 to 72 hours, and then take it out of that temperature, because if you have tryptic soy agar plate in that 30 to 35 degree range temperature for a full 5 to 7 days, you're going to see the growth media completely dry out. It's going to shrink on you, and it's potentially there could have been something that was growing on it, but because you essentially cooked the growth media, you didn't allow anything to grow on it. So again, 797 says if you are going to use tryptic soy agar for both bacteria and fungi, you have to use 2 different temperatures. For the 797 revision, 20 to 25 degrees just so happens to be room temperature. That's anywhere from like 68 degrees Fahrenheit to 75 degrees Fahrenheit, roughly. But since we're still going by the old 797, it says 26 to 30 degrees Celsius. So there you have it. The malt extract agar and Sabra dextrose agar are to isolate fungi. They're specifically formulated for fungal growth, and but the same timing still applies to this. Same temperatures still apply to this. They're just, fungi are just slower growers, even if you give them media that they especially like. So that's just the way it is. Environmental monitoring is a quality control to show the level of quality assurance of your compounds. So that's the difference between QC and QA. Environmental monitoring is a tool, a control that you're using to show the overall quality assurance of your operation. Without EM, there's no quality assurance. And as I said before, FDA may ask to do a recall of all batches. EM is important, and it should be done regularly, depending on risk level. How often is going to be dictated by risk. So what's a good schedule for performing environmental monitoring? I don't know. It depends. It depends on your specific operation. Evaluate based on risk to your patients. Are you starting with non-sterile ingredients? Are you making something that's going to be injected intrathecally? You should ask these 2 basic questions. If a compound was contaminated, what would happen to the patient? That's the severity of the effect. And if you had a contamination of a compound, would you be able to pinpoint where the contamination came from and be able to prevent it from occurring again in the future? And that's where probability comes in. So if you can't answer those 2 questions, then you're probably not doing enough environmental monitoring. So keep those 2 questions in mind. Again, this all comes back down to the patient at the end of the day. We want a quality assurance program to assure the level of quality of our compounds so that our compounds are safe, effective, potent, pure, and so on for our patients. They should be getting the right ingredient, the right dose at the right time, every single time. And without contamination, I should add. So what to do if and when you get this? Now, this is a little bit of an exaggerate. This is a stock photo I took from Adobe stock. Thank you, Adobe, for the very good image. But it looks like you've got some fungal growth on there, maybe some bacterial growth. But if you have a contamination and it exceeds your action limits, now what? What do we do? Well, you're going to initiate your investigation, but there's a stepwise process to this. So don't worry. I'm gonna walk you through this, and it's actually quite simple. Unfortunately, USP 797 is not really a how-to guide on investigations. It tells you that you need to do an investigation. Okay, well, how do I go about doing that though? And there is a methodical way to go about it. I, in particular, like Six Sigma's DMAIC framework, and a few other systems that I'm going to be talking about during the presentation. You know, if you've heard of Six Sigma, and I'm sure you've at least heard of Lean Six Sigma, they're manufacturing frameworks for decreasing errors and eliminating waste, basically, to summarize in just a really short paragraph. In compounding, I feel like Six Sigma's DMAIC framework is largely unknown. And without a proper CAPA system, after correction, you need to focus on prevention to improve the processes. So you really need a framework to do this all in, that being DMAIC for your investigation, and for your process improvement, having a good CAPA system in place. So investigations of discrepancies kind of go like this. So you have an out of OOS, out of specification, either EM, sterility, or potency. You're going to want to define the problem. M, measure. You're going to look at metrics of the process and or other data, complaints, lab results, environmental monitoring, and look at the severity of the effect. Again, this is where risk is always coming back into the conversation. But if you don't have these metrics, if you don't have the environmental monitoring, like we're talking about in this particular scenario, you don't really have anything to go on. So it's going to be really difficult for you to do an investigation. If something has got to the point of the patient, it's already too late. You can do an investigation afterwards, but the damage is already done. So what we want to try to focus on is preventing that before it gets to the patient. And that's what environmental monitoring sort of allows us to do. Next, analyze. You're going to be finding the root cause and implement different solutions. You're going to sort of hypothesize what the root cause was. You might have 3 different root causes that you kind of narrowed down and came up with. And you're going to test those different ones one at a time to see if it's actually fixing the problem. In the improve phase, you're going to use the corrective action that or actions that you selected, and you're going to want to make sure that they're under control through your control phase, and implement preventative actions for continuous improvement. So the overall goal of this whole DMAIC, DMAIC, is to decrease process variation. That's what it all boils down to. I've kind of already gone through a lot of this stuff, but let's look at it in terms of environmental sampling specifically. So define the problem. We have a couple different metrics. We have viable sampling, total particle counts. They're able to prove to us whether our clean room is under a state of control. Where was the problem? Was it in our hood? Was it in the room in a particular location? Was it the operator? Establish boundaries. The boundaries are sort of already established for us with action limits and contamination recovery rates. Process variability. So what are all the different variables in your process? Going from point A to B, going into the clean room, gowning up, getting ready for a procedure, bringing all your materials in, and then performing the procedure, cleaning everything up. There's a whole bunch of variables in there that you may or may not realize that all can have an effect on contamination. And of course, with this, you're going to be able to calculate the expected benefit by decreasing process variability. You're lowering the chance of contamination, and hopefully, God forbid, any litigation fees or anything like that. So here are a few of the metric tools for measure, the M part of DMAIC. Cause and effect diagram, which I'm going to show you on the next slide or two. A process map, which I just kind of like really quickly, went over. You're going to go into the clean room, you're going to gown up, you're going to do the compounding. A process map gives us a really clear picture of all the things that we're doing during a process. And what it can also do is identify the control points, the points at which you want to put in specific quality controls to mitigate any kind of risk for contamination at that particular point. So for instance, bringing in materials into our clean room, that's a point for contamination. So what are we going to do to mitigate that? We're going to wipe off all of our materials with some kind of disinfectant, or a sanitizing agent like alcohol, isopropyl 7030, and we're going to make sure that we're maybe even periodically sampling those materials to make sure that process is working correctly. And again, data collection, if you particle and EM data, if you're not collecting that data, again, it's going to be really hard to do any type of investigation. Some of these other ones that are kind of grayed out, I'm really not going to go into any of those. Value stream mapping, process control charts. These are all process control charts. Are the Excel spreadsheet I showed you earlier has an aspect of control chart to it, using statistical measurements from inputs that I'm putting into the spreadsheet. So define with EM data, you look at samples on a date of occurrence. Without EM data, I don't know, I'm not sure what you would do. If sterility was the issue, you could ID the microorganism. If it was actually in your products, you could identify the microorganism and find out the testing results. Let's say, for instance, for our example, for our purposes, that it was a Penicillium and Bacillus species that was identified. So we've got 3 CFUs of Penicillium, which is a fungus found on our ISO 7 anti-room viable air sampler. So in the air, Penicillium was also found on the right glove of the pharmacist tech or pharmacist that was compounding cyanocobalamin. There's also 1 CFU of non-sporulating hyaline fungus found on a surface of an ISO LFAW, laminar air fluid. 1 Penicillium on the left glove of the person compounding trimix, which contamination of trimix, if you know what trimix is, that could be a very bad day for some gentlemen. And then you have 1 CFU of bacillus, which is a gram-positive, in your ISO 7 hazardous materials room table, so your staging area. So have we exceeded any action limits here? We actually have exceeded the action limits for, I don't think any of these. Let's see, ISO 7, ISO 5, on the surface of ISO 5, no. 1, no. So in this scenario, we actually have not exceeded any action limits according to 797. However, somehow it did get into the sterility results of one of the compounds. So we're going to initiate a CAPA. Here's phase 1. Phase 1 is document a problem identification. It sort of goes along with DMAIC as well, by the way. So as you're doing DMAIC, you're also going to be filling out and putting in portions of this. So what is the issue or deviation that has occurred? There is a contamination of a compound preparation. How is the problem identified? Sterility testing. Create a problem statement that describes the issue in detail and what exactly needs to occur for the problem to be considered remediated. Sterility testing indicated growth of 2 microorganisms in the final preparation. You need to find the cause and implement solutions to prevent in the future. What's the scope? It's a very serious issue of contamination control, and will be assigned to the quality assurance team to identify possible causes and implement solutions to prevent reoccurrence. Phase 2 is the impact assessment and risk analysis. How much did this actually impact your operation? Well, potentially, if that drug got to a patient, that could be a pretty serious infection, depending on where it's being injected into. So I'm going to put that as a high level of risk. The contamination was isolated to 2 preparations, vitamin B12, a sub-Q injection, and trimix of penile injection. Based on the risk level of this problem, the timeline for remediating this issue will be within. The problem needs to be identified and resolved immediately prior to any further compounding taking place to prevent this issue. So again, this is a CAPA form that I created myself, going through each of the 8 phases of CAPA. And in doing so, again, we're also filling in the gaps of DMAIC. So in the analyze phase, we're going to make sense of all the data. We're going to look at the 6 M's of contamination. So this is where we're going to look at a fishbone diagram on one of the next slides here. We're going to use the 5 whys technique, which will help us find the root cause of the problem. And we're going to rely on statistical analysis, statistical process to control in this stage. Analyze also, we're going to be looking at qualitative versus quantitative, what organism and how many. We may look at the media type, the sampling type, of course, the methods of sampling, historical EM data. Is this a trend or is this just an isolated incident? What about the particle count data? Was the particle count data really high for that period of time? So here's the 6 M's. This is where you can really boil down and find the root cause of your analysis. So actually, let's see. I have the 6 potential causes of contamination on this slide. On the next slide, I have it in the 6 M's. They're really the same thing. This is in more common terms: raw materials, personnel training, cleaning, sanitization, process, facility. These are all the different areas that you're going to look at. And then each of those has subcategories that you're going to look even further into. So again, based on what the actual organism is probably going to give you a direction of where to go within these 6 different areas. So 6 M's is just materials, manpower, methods, Mother Nature, management, machinery. So it's just the same thing, just labeled a little bit differently. So again, we're still in the analyze phase. Penicillium is a fungi found where, you know, it's found in a lot of different places. It's very prevalent. Bacillus gram-positive, found where, they're also pretty much found everywhere. This is really the most oversimplified chart that I could make. Generally, gram-positive are coming from humans, and I feel like there are probably a couple microbiologists on the call today, so don't beat me up too much. But gram-positive typically comes from human. Gram-negative, typically you're going to look at soil and water sources, and fungi, molds, and yeasts is variable. You know, could be from soil or water sources. So this is another chart that looks at the different areas of the clean room and what are typical microorganisms that are going to be found on those areas or in those areas. This is from a book called Clean Room Microflora by Tim Sandel, who's one of my favorite microbiologists. Tim Sandel, remember that name. If you ever want to learn more and take a deep dive on this subject, he's a very prolific author. He's written a ton of papers, several books, and you know, he's a microbiologist, and you know, he comes from the UK, so he's across the pond, but his information is excellent. Also has a YouTube channel. Check out his YouTube channel. I'm not getting any paid endorsements or anything from Tim Sandel, by the way. So it's just I like him. So organism rate of occurrence. So this chart is really showing us that if we have a gram positive, it's highly likely on a clean room surface, clean room equipment, air, not going to be found in water, high likeliness to be found on people and in gowns, and materials brought into the clean room, maybe not. Gram negative, you're typically not going to find those on the clean room surface, wall, or floor, generally speaking. Clean room equipment could be anywhere from high to low, maybe not. Gram negatives typically you're not going to see those in the air. There's a lower chance for that. In water, there's definitely a high chance for finding gram negative. A little bit lower chance of finding it on people or gowns, and variable with materials being brought into the clean room. And then fungi is kind of moderate across the board. So, you know, fungi is tricky. It can find its way into a clean room through many different ways. So this is just another one of those good charts I pulled out of that same book, Clean Room Microflora by Tim Sandel. So here are the particle count. I've kind of already showed this slide or on a slide. These are the ISO class and the limits for particle counts of 0.5 micron in a particular ISO class. By the way, I will just say that if you're testing your ISO 5 primary engineering control and you're coming even close to 3,520, there is something wrong with your engineering control. Your engineering control should basically be at 0 particles at all times. When there's operators and they're operating, you might have, it might get up into the tens or hundreds of particles. But if you're getting into the thousands of particles in your primary engineering control, there's definitely a problem somewhere, either the HEPA filter or issues with how the operators are behaving. Same thing goes for all these other things. These are the absolute top limits. If there's close to 352,000 in your ISO 7 or 3,520,000 in your ISO 8, if there's anywhere near those numbers, you should be alarmed that you're passing, but you're not really passing, if you know what I mean. So, and I've shown this several times again, your action limits for your air sampling for your different ISO classes. So what's the relationship between particle counts and viable air sampling? I've kind of already alluded to this already. The size particles that you're looking at is 0.5 micron. Why? Because that's the size that microorganisms usually travel on. Setting alert and action limits for your particle counts, maybe if you have a particle counter and are using that on a regular basis, say daily, and all of a sudden you're getting really high particle counts, maybe that could be an indicator for you to do viable sampling, surface and air sampling, to then figure out what the organism is and how to remediate it. And what are the levels of viables exceeding action limits? We've kind of already done, looked at that a whole bunch of times. Is there an algorithm for sampling? This is what I just kind of said. If you're doing particle counts continuously, if it exceeds X, then we're going to perform viable. So that's just a suggested algorithm for maybe using particle counts in combination with viable air sampling or viable surface sampling. So then we move on to phase 3 of the CAPA. We're going to use the 6 M's, and we're actually just going to document. So in the measurements, 3 CFU found on the ISO 7 air sampling, 1 CFU found on the right glove of the operator, 1 CFU found on the left glove of the operator doing trimix, 1 CFU found on the ISO 5 surface of the laminar airflow hood, and 1 bacillus CFU found in the ISO 7 HD buffer room table. Materials, no contamination was found on any of the raw materials. Man or personnel microorganism growth found on gloves of the operators affected preparation. So remember, touch contamination is the highest source of contamination, or the highest risk of contamination, I should say. So then we look at working properly, since we found an air sample in the room and the surface of the LAFW. May need to clean areas and certify engineering controls are working properly. Also need to look at environmental controls for temperature and humidity, and any areas in question, since penicillium was a mold that was found. And methods, processes, and procedures, since multiple organisms were found on the gloves, air, surface, need to ensure operators are following procedures for gowning, disinfection gloves, disinfection of surfaces, and adequate intervals with proper agents, observing contact times. And Mother Nature, penicillin and bacillus are naturally occurring microorganisms in many environments, and could have been brought in on materials and or operators. The 5 whys, I'm not really gonna read through all of these, but basically it's asking the question why 5 times to boil down to get to the root cause analysis. So the root causes were identified to be lack of infrequent training on contamination control, aseptic technique, and observational competencies, improper contamination control, not wiping off materials prior to entering the clean room, gloves not being sanitized frequently enough, and the ISO 5 PEC and other surfaces not being cleaned and disinfected frequently according to policy. So find possible solutions using brainstorming communication and evaluate possible solutions. This is where you're going to want to involve those people that are directly involved in these processes. You really want their input on this stuff because they're intimately involved with the process. They know the process like the back of their hand. And then a manager, you managers should be the one overseeing the project overall. So improve, we're going to look at storage and staging. We're going to reposition personnel. Maybe there is too many people. Maybe they weren't properly gowned. Training, were SOPs in line with practices? Were we actually training as much as we should have been? Facility, the storage area, which is a high traffic area. Maybe we should put all of our materials in plastic bags, and that way we only have to wipe off the plastic bags to go into the clean room. Cleaning and sanitization, maybe our frequency, agents used, or contact time wasn't being observed in our process. The compounding process, the environmental monitoring process, cleaning process, gowning, material transfer, and environment, the amount of stuff that's actually in the clean room. I know in a lot of health systems, and I've been in many a hospital clean rooms, they're used as sort of as storage closets for a lot, like basically all the drugs are stored in there. There's papers hanging up on the walls showing people how to do hand hygiene properly and whatnot. You know, all that is indicators that you're not cleaning your clean room properly or frequently enough, and that the more stuff that's actually in the clean room, the more particulate that's in the clean room, and the more you're going to have to actually clean when you do your monthly clean. So I'm a big advocate for basically having nothing more or less in your clean room. Bring the stuff in as you need it. So improve raw materials being wiped off, too much stuff in the clean room. Personnel retrain operators on technique, gowning, and behavior. Maybe there's going to be some SOP changes in terms of how often we're training. Maybe we're going to do more sampling of personnel after this to see if the process is under control. Maybe we're going to sample periodically some of our materials that are being brought in to see if they've been wiped down properly. Facility and engineering controls, we can test controls, or we can also, and this is where I'm going to bring Rich in on the next slide, actually in 2 slides, I believe, where we can actually utilize a piece of equipment to help us mitigate any issues that we're having. So phase 4, the correction, containment, improvement phase, all operators are directed to go through gowning and glove fingertip sampling again. Need to pass with 0 CFU. Operators were retrained on policies for aseptic technique, sanitization of materials, and cleaning areas, your ISO 5 areas at 30-minute intervals during continuous operation. All operators must pass a media fill prior to compounding continuing. As a temporary mitigation step, we'll also employ Plasmair's Guardian system to help clean up the air immediately in the buffer room, which should have an immediate effect on the overall state of the clean room. So it was identified that the operator had not sanitized their gloves in between exiting and entering the ISO 5. materials were not being wiped off properly prior to entry into the next area. And material transfer needs to be, you need to wipe them off at every stage of going into the next area. So from your general area to your anteroom to your buffer room to your ISO 5 PEC, you're going to wipe off the materials and disinfect at each one of those stages. And then the general environment also just needs to be cleaned up. There is too much stuff in the clean room, and Plasmair really helped with this. So, Rich, I'm going to let you take it from here. Maybe introduce yourself, tell us a really quick word about yourself, and then let's move on from there.
Awesome, very good. Thank you, Seth. Excellent presentation. I'm just watching the participants. There's 62 now, and if I start talking, they drop off. I don't know. As you know, Seth said earlier, he's a microbiologist. Neither am I. I'm not a pharmacist either. My classical education was in mechanical engineering. So my first 15 years was in semiconductor manufacturing and clean rooms, class 1, class 10, class 100 clean rooms. Very high levels of purity and cleanliness in those spaces. That was my first 15 years. The last 15 years, I've been involved with pharmacy automation, IV workflow, robotics, and currently working with Grifols. One of the things that you said earlier, Seth, was, I just wanted to hit on about the use of particle monitors, especially the non-viable continuous particle monitors. With Grifols' experience, we have over 2 million square feet of FDA-regulated CGMP clean space, entire rooms that are ISO 5,000 square foot, 500 square foot rooms. The entire ceilings are HEPA filter. The walls are low air returned. So very impressive environments. And all those rooms do have particle monitors, and they're continuous non-viable particle monitors in conjunction with the viable sampling as well. And then we get into our customers who are building 503B clean rooms, as we're a clean room provider. Those folks are using particle monitors as well. Usually at the workspace level, in other places, that's key. And then our 503A hospital pharmacy customers, about 10% are using particle monitors, more of if it's a CGMP type process. So, we do see that. So, but that's not what I'm here to talk about. You asked me to come in and talk about Plasmair. So this is a technology that was originally developed for the International Space Station years ago. And AirInSpace, which is based out of Versailles, just west of Paris, about 30, 40 minutes. And they've developed this technology to be utilized mostly in patient areas. So in Europe, where they have mostly, I'd say, immune suppressed patients, for example, bone marrow transplant. Those are the places where you'll find Plasmair in use in Europe. And during COVID, they shipped a whole bunch over to Asia, specifically into China, where they were helping out with the COVID. In the U.S., Grifols is the exclusive distributor of the Plasmair system, and our primary use case is in hospital pharmacies for remediation, mitigation. We also use them for temporary clean rooms as well. So I'll go over a little bit about that. The system is pretty cool. It's a size of a large refrigerator, and it's on casters, so you can roll it right into a clean room, plug it in. Our engineers are typically involved with the install. They'll program the system based on the room size and get the system up and running. And it's a really unique technology. As I was mentioning earlier, it's a HEPA filter with microbial destruction. Does a really good job of killing any type of airborne microorganisms. So it's a multi-stage reactor, and I have a diagram in the next slide that shows how that works. And what it uses is a high energy electrical field across the plenum and where air can flow through. And what happens there is it just effectively burns at a room temperature all the microorganisms. So as I said earlier, it's remediation. So if you have a clean room that's having airborne viable contamination, that's where a lot of our customers use the Plasmair system. They also use it to mitigate contamination. So if you have like a 503B or say it's a larger CGMP type clean space where you have 6, 7, 8 hoods or more, and you have 6 or 7, 8 or more technicians walking in and out of that space, that's where you can usually use these systems as well, in conjunction with your HEPA filter air is supplied from the ceiling above. And I'll also have a picture of what we use in our temporary clean room. So you can advance the slide, Seth. Thank you. So this is the diagram with a 4-stage reactor. What's not included in that 4-stage reactor is underneath there's a filter to just clean out the gross contamination of dust bunnies. And then there's a fan filter unit, blower unit that's modulated. We can control the airspeed based on what's required for CFM output outside the Plasmair system. And I'll show you in a couple slides. We can duct these as well and provide positive pressure across multiple spaces. It's pretty cool in that perspective. So our engineers will figure out what the sizing of the unit is when they're programming the system in. And we'll try to boost the air, the CFM to accomplish 20 to 30 air changes per hour in a clean room. That's our goal. So the first stage is the plasma module. And as I said earlier, there's an electrical field applied across the grid. And as air flows through that grid, all the microorganisms in that air get fried or zapped. And then there's a high energy field, HEPA filter that captures all those dead bugs that fly through. And then we have a catalytic conversion system. And the reason why we use that is because sometimes in the plasma module, we'll have O3 generated. And then the last one is the chemical filtration modules to cancel out all the VOCs that could be inside the space. So the unit's very quiet. As I mentioned earlier, we use these a lot, or in Europe they're used a lot in patient areas, and they're actually rolled in from room to room. Typically, when we put them in a clean room space, whether it be in a buffer or an anteroom, that's where they stay for the remainder of the time and use of that clean room. So you can advance this slide, please, Seth. Thank you. These are the various microorganisms. There's more, but just to give an example, we have bacteria, viruses, spores, which we're more familiar with in clean rooms. Fungal spore, and it has in most of these instances a 99.9% single pass biological reduction rate. So what that means is, as it goes through the machine once, or the system once, 99.9% of the microorganisms are killed. So, and typically we'll do 30 to 20 air changes per hour inside a clean room. You can advance this slide, please. Thank you. So I got a couple examples. This is a clean room up in the Northeast, and they had a culmination of a perfect storm. 3 different things happening. You can see in the there's a person on the phone. This is their anteroom at a 2-person workstation. There's computers there. Also, there's a very large refrigerator storing HC drugs inside that space, and then there's also a rack of supply as well. So, as Seth was saying earlier, you don't want all that supply in that space, but this was a clean room that Grifols was originally looking to get involved with. They decided to go another direction because of costs. So they ended up having issues almost on opening of airborne contamination. So very, very short after opening. So the air changes per hour, which is something I see in my everyday life, is airflows are typically under designed inside clean rooms for IV compounding. So with Grifols engineering, we typically go to a much higher level. But in this situation, the customer was at a very low level, just passing the ISO 7 requirements, but only getting 30 air changes per hour. So what we did is we installed the Plasmair. When I say installed, it really entails plugging it in, doing a wipe down on crating, taking out the plastic, but seriously, just rolling it into the space, plugging it in, and then it boosted the effective air changes per hour over 50. And so they were able to continue operations, which we then designed and built their next clean room. So funny story is when the director of pharmacy called me and said, hey, okay, we're closing down the old clean room. We're opening up your new one, Rich. Can you take this Plasmair back? I said, yeah, sure. We'll figure that out. And called me, I think, a few days later and said, hey, let's keep it because we need to use it in our other main pharmacy. So they had airborne that they wanted to, airborne viable that they had to take care of. So they moved the Plasmair. Again, they just rolled it down the hallway, plugged it back in. And our engineers actually helped out with that. So next slide, please. Here's another example. This is a customer of ours who having very similar issues inside the anteroom, very common. They were down to 30 air changes per hour, which is passing the ISO 7 USP 797 requirement, but just not doing the job when you have a busy anteroom. The design of the room is not so great either. They had a lot of supply. There's a workspace in there. When we design our clean rooms, we use the anteroom as access to the buffers only. And workrooms are for work and anterooms are for access to the buffers. So what we did is we installed the Plasmair Guardian. So there's two units. There's a Guardian, and then there's the Sentinel, which is a smaller unit. So depending on the size of the room, we'll figure out which one to use. And so we installed the Plasmair Guardian, and you could tell by the CFU counts, it reduced the number of CFU counts for that space. The positioning also is important. The way the unit's designed, it throws air up and across the room. You can see at the top of the unit, it's louvered. So it sucks air from the bottom, which becomes effectively a low air return, which is very important in designing clean spaces, to pull the air from the bottom and blow the air out the top. And positive pressure environments to try to have that air aimed out the door towards the opening to, say, a workroom, for example. And negative pressure environments will change that. And we also want to throw that air across the length of the room as much as possible. So we'll make suggestions to customers to move items around, or if you remove a shelf or remove a hood, if possible, and able to get the system up and running. But it's very versatile in where it fits. Next slide, please. So this is a mitigation example. We had a customer who built a brand new Grifols Mysterium clean room, and it was designed really well. No troubles with the airflows at all. But the customer said, we've had issues in the past. It was a shared air handler, for example, and they were just concerned with their experiences in the past using shared air handlers, that they didn't want to take any risks for a new clean room. So they decided to put the smaller units. These are Sentinels that I mentioned earlier. They decided to put the Sentinels inside each buffer. And so those Sentinels could handle a 100 square foot room fairly well. And that worked out very well for us and for the customer. Next slide, please. This is one of my favorite examples because it's really taking and leveraging the unit's capabilities. So this was a clean room in a Boston area, and a temporary clean room, I should say. So we were building this customer's CGMP space out, and they had the need for a temporary clean space while they were operating. While we were building out their new CGMP space. So this is a 4-4 foot hood operation, and they were able to support an 800-bed hospital. So very busy area. You can see at the top of the slide that there is it's pulling air from the HVAC above. And you can see that drop ceiling right there is actually the office space or the conference room space. So this was an old conference room, and we put in our clean room materials and designed it for this particular customer. And what it did is it pulled air from that tepid air from the HVAC system, cleaned the air, and then put it into the buffer. So that was a non-HD buffer, and then across the anteroom, and then out to the workroom. So just outside that workroom area, it's in a sub-basement next to dietary. So there's a kitchen there. There's a morgue, a dumpster, needle exchange program, and it's not the cleanest space. So we were able to achieve their ISO 6 inside the buffer, and so it's very clean. Never had any issues on the recertifications, so it worked out really well for that particular customer. So what I liked about this design here is it's using control. So the fan speed inside the unit is controlled by pressure sensors inside the rooms. So we were actually maintaining 0.02 inches of water or more in the buffer to the atrium out to the workspace. So a pretty unique operation there. Seth, any questions? Did I hit on all the topics, or?
I think you hit on all the topics. I think you did a good job. Yeah.
All right. Thank you. Thank you.
Yeah. Thank you, Rich. I really appreciate it. So yeah, I just got a few more slides. I'm just going to go through really quickly here. I'm actually going to skip several of the slides, but I want to hit on the high points. The last portion of this is the control, arguably the most important part of Six Sigma. This is where you're going to involve checklists, document updates, maybe updating SOPs, implementing new quality controls, monthly review meetings, training, maybe implementing more environmental monitoring. You're going to want to ensure you're maintaining that new baseline of performance that you've set. And again, this is a preventative. This is the preventative action part of it. So phase 5, you have a corrective action, preventative action, control. Excuse me. If you have a risk-based EM program to identify when excursions occur, you include particle counts more frequently, maybe. Corrective action, plan your compounding process. It's all about workflow. So you don't have to exit the buffer area ever to the anteroom or going into any lesser class ISO classified area. Minimize leaving the ISO 5 PEC. And if you do, ensure that you're frequently sanitizing your gloves. Implementation phase, this is phase 6 and 7, where you're going to implement the corrective action, and then you're going to verify through your maybe new controls, new process controls that you put in place, glove fingertip sampling of the materials, maybe cleaning more frequently, more sampling of your ISO 7 and ISO 5 areas. And how often will the solution be measured to ensure the effectiveness, verification of the effectiveness? And in this paragraph, I basically have a step-down approach that we're gonna, for a period of 60 days, we're gonna do this on a daily basis. If at the end of 60 days, we're gonna back it down to not doing it as frequently. if following another 60 days, the weekly monitoring is still consistent, this will be extended to just once per week for a random batch. So I'm basically using a step-down approach to ensure and verify the effectiveness of our solutions. Preventative action summaries. Operators are glove sampled post-compounding, initially increased EM, decreased based on results, which is the control portion. Workflow changes, staging and sanitization, EM performed to confirm. Media fills more accurately reflected the actual compounding procedures. Training records were done on time per policy. Cleaning process, agents, and frequency were looked at and ensured that we were doing it according to policy with the proper contact times and the proper frequency. And we actually ended up keeping the Plasmair air system because it was such a great system at cleaning up the air in the room that we just decided to keep it. So then you're essentially, the last phase is the closure of the CAPA. You've concluded that the CAPA did in fact work. You've implemented new policies and procedures, and you are then signing off on it. This is just a really quick look at statistical process control. This is where I kind of modeled my my own spreadsheet after. This is available free at asq.com/quality-resources/data-collection-analyst-tools. And you can download your own statistical process control chart. Some final thoughts: implement corrective action, preventative actions discovered through DMAIC. Document this process. If you don't document, it didn't happen. So it's very important that you have a proper way, either electronically or by paper form, of documenting the CAPA process. And any changes to pertinent SOPs, you have to be worried about change management and making sure that you're not necessarily just throwing out all your old SOPs and shredding them. A part of change management is putting in the changes in place and storing the records that are outdated. Train on SOPs, incorporate into future training, and then document that this was all done with all the operators. Responding to 483s, I'm not really going to go into this. This was a relic from the old presentation, but if you do get a 483, you have to respond within 15 days. Do not be argumentative with the FDA. Just say, this is how I'm going to correct this. This is the timeline I'm going to correct it in, and that's it. And again, just clearly state all your responses. And I wouldn't disagree necessarily with the FDA. Those disagreements typically don't end so well, and usually end up in a warning letter situation. So just read and heed. So this whole contamination control prevention, it's all about prevention. Don't use your clean room as a closet. Wipe things down with IPA and or other disinfectants. Bring in only what's necessary into your clean room. Otherwise, it should be rather empty. Training, of course, is a huge part of this. Engineering controls, and of course, environmental monitoring for continuous quality improvement. Across the board, some of my final thoughts: the drug supply chain should be patient-centered. Maybe we should have more transparency across company lines. Manufacturers 483s, while you can put in a Freedom of Information Act request to get any 483 you want, they're not readily available like they are for hospitals and 503As and 503Bs. They don't just publish those online, unfortunately. Should we have an information exchange to increase quality? Again, this is talking more about going across corporate lines. The devil is in the details. Analytics and metrics. Data collection is key to all of this stuff. Data should be used to support quality, detect variability, and improve processes, period. Let's see. And then I'm just going to go right to the last slide. We are right at 3:03. And I believe I answered, let's see, I've got one unanswered email or message. Does anybody have any questions? Feel free to ask them now. You can unmute yourself if you like. If you do have any questions after the fact, for the people that are left here, thank you for hanging on for the full 2 hours. I really appreciate it. And if you have any questions, feel free to email me or Rich at those email addresses. Happy to answer any questions. Rich, there's a question that came up about. I'm gonna, Rob, if you could email Rich directly about that, he can give you more information about that. Because to be totally honest with you, I actually don't know the cost of the Plasmair, and I think there's 2 different models, and there's different options for you, but I'm not 100% sure about the cost of Plasmair.
Yeah, I can give you rough. The big one is about 40,000 or so. A little less than that, and then large and the smaller one's around $30,000. So then there's maintenance fees as well.
Like I said, this whole presentation's been recorded. I will be publishing this on my Vimeo YouTube channel, and I'll definitely put it out there. You'll get a notification via your email, and it'll probably also be on LinkedIn as well too. So there's going to be plenty of opportunity for you guys to catch this again. But if there's no other questions, which I'm not seeing any other ones that I haven't answered, I will bid you guys a good day. And again, thank you very much for attending. I hope you got a lot out of this, and thanks. And thanks to you, Rich, for putting this together with me. I really appreciate it.
Yep. Thank you, Seth. Thanks for the time. Appreciate it. Thanks, everybody, for joining.
Everybody have a great day.